Okay, so we're going to talk about the organization of the periodic table. So the definition of a periodic table is an arrangement of elements in horizontal rows, those are also called periods, and vertical columns, also called groups. Okay, and the periodic table exhibits a repetition of properties. It means that there's a repeating pattern that is observed in a variety of different trends. Okay, the very first periodic table was organized by Mendeleev and Meyer, and the elements with similar properties were in the same column, the same groups, and the elements were arranged in increasing atomic mass. Okay, so there were a lot of different discrepancies arranging them based on increasing mass. And so the modern periodic table actually arranges them in the atomic number, right? The number that's on the periodic table for each element, counting up. All right, and the elements are classified as metals, nonmetals, and metalloids. All right, so some the basic layout of the periodic table. Okay, so this is just a very generic sketch of the periodic table here. Okay, so remember our rows are also called our periods. So the rows going across the periodic table and the columns are going down the periodic table. Those are also groups, or another way that you can kind of classify them are family. So going down, they're family, meaning all of those elements in the same column have similar properties. Okay, lots of similar properties. All right, so there's kind of the three classifications. We have the metals, the nonmetals, and the metalloids. Okay, so kind of first talk about maybe the metalloids first, because then we can differentiate the metals and the nonmetals from them. So over on your periodic table, if you were to pull open the one that I gave you in class, right, there is kind of like a staircase that is over here on the right hand side of the periodic table. The ones that I've kind of circled in black here, those are the metalloids. Okay, so typically what we say is there's a staircase here, and the ones that border the staircase are the metalloids. Okay, but these ones here are the metalloids. Okay, and so that's kind of denoted what I have right here. All right, so to the right of the staircase, okay, right of the staircase, these are all the non-metal atoms. So non-metals, they are not metals, okay? And to the left of the staircase, okay, over here, everything to the left of the staircase, these are all metals, okay? And then there's some more specific, names of some metals that we can classify over here, okay? So the first column on the periodic table, these are called the alkali metals. Okay, all of them in that same column. And in the second column, these are the alkali earth metals. Okay, so those are all the metals that you find in the earth. Okay, and then in this middle section here, this block section, kind of like in this yellow part right here, these are called the transition metals. Okay. All right. So a couple other specific organization names. The last column on the right of the periodic table, these are all noble gases. We call these noble gases. They have a complete shell, a complete octet of electrons, okay? And they are inert gases, meaning they do not react. The column right to the left of the last column here, these are called the halogens. Okay, so starting with fluorine at the top and going down. Fluorine, chlorine, bromine, iodine. Okay, so halogens right there. And then the top of each of the columns following that, we typically sometimes will say the oxygen family, right? So this starts oxygen family, nitrogen family. Remember, everything in that column has similar properties and similar electron configurations that we'll talk about here shortly. Okay? All right, so a couple other just basic things to discriminate between metals and nonmetals. So metals are mostly solids that you kind of already are familiar with. They're shiny. They're really good conductors, and they're malleable or ductile, which means that they're kind of soft and flexible. All right, and in a chemical reaction, metals, so all of these atoms here, they will always want to lose electrons. They'll always give up electrons in a reaction. Okay? The nonmetals, they can be solids, liquids, or gases. They're usually dull in appearance. They're very poor conductors. They're brittle if they are solids, and they will gain, share, or take the electrons from the metals. So the nonmetals will take the electrons from the metals will lose or give them up to the nonmetals. Okay, and then the metalloids, kind of like a mixture of properties between the two, both metallic and non-metallic properties, and we know these as really good materials for semiconductors. All right, so the periodic table is also a couple other things that we need to talk about in terms of, there's two different types of groupings of elements. The first one is kind of a group A elements. Okay, so these are groups 1 and 2, so that's columns 1 and 2, and columns 13 through 18. So there's 18 total columns on the whole periodic table. Okay, so column 1 and 2 and columns 13 through 18. So typically these numbers are at the top of the periodic table, but here, just because there's a lot going on up here, I have the numbers listed on the bottom of the periodic table here. Okay, so column 1 and 2, and then 13 through 18. These are called the main group elements. Okay, so they're typically labeled as A, so this would be like 1A, 2A, and then it would be 13A, 14A, 15A, and so forth like that. Okay, these main group elements, okay, tend to be largely predictable with the trends that we're going to talk about, like so size of atoms, electronegativity, things like that. Okay, and so they kind of follow the trends. Okay, the second class of grouping of elements are the metals that are between the main groups. So this is not correct here. This should be 3 through 12. Okay, so there are 10 columns, 10 families, or not really families, 10 columns of transition metals here in this main section. Okay, and also the inner transition metals are also classified as B. Okay, so these are labeled as B, so this would be 3B, 4B, 5B, 6B, up to 12B. And so there's 10 of them, 10 columns right in here. Okay, these typically do not follow the trends of the periodic table, and so that's kind of why they're labeled as B. Okay, another important thing is atoms in the periodic table are always neutral, just like we talked about when we were figuring out number of protons, neutrons, and electrons. Right, that charge in the symbol notation is always understood that there's a zero charge, that it's neutral. Okay, and then some elements are diatomic elements. Okay, so it's not just when we talk in terms of these particular elements like hydrogen, we kind of always refer to it as hydrogen, but when we say hydrogen, we actually mean H2. So it naturally exists as a molecule, as a diatomic together. Okay, so there are 7 of those atoms. That's hydrogen, nitrogen, oxygen, hydrogen, nitrogen, oxygen. Okay, so hydrogen, nitrogen, oxygen, and then the halogens. So fluorine, chlorine, bromine, iodine. Okay, so they exist as H2, N2, O2, FF2, Cl2, and so forth, Br2 and I2 there. Okay, so when we say diatomic elements, or they come up in a problem, it says, oh, how much hydrogen is such and such made, okay, in grams. It's not just H, we're talking about H2, so it's automatically understood that it's the H2 diatomic species there. Okay? Okay, so we use electron configurations, I'll commonly abbreviate ECN there, to describe how an electron occupies orbitals, or how the orbitals are being filled with electrons. Okay, so quantum mechanical theory describes the behavior of electrons in atoms, and this electron configuration is going to describe how the electron occupies the orbitals in an atom. Okay, so electrons in atoms exist in orbitals, right? Each energy level and type of orbital in that level can only hold a set number of electrons before another orbital must be added for the electron to reside in. So if you recall that s orbitals can hold 2, p orbitals, there are 3 different types of p orbitals, px, py, pz, and each of those can hold 2, so it's 2, 4, 6, so there can be 6 electrons in p orbitals. D orbitals, there's 5 different types, 2, 4, 6, 8, 10, so there could be 10 electrons in the 5 different types of d orbitals. And then the f's, there are 7, so then that would mean there's a total of 14 electrons that can go in the f orbitals. Okay, so as you are calculating the number of electrons there are in an atom, right, those electrons can only reside in certain orbitals, and certain orbitals can only hold as a certain amount, so then you would have to add additional orbitals for them to reside in. Okay, so the description of orbitals occupied by electrons, we call that the electron configuration. Okay, all right, so an example of an electron configuration, we just use the most simplest example here is with hydrogen. So hydrogen is the first atom on the periodic table, and the electron configuration would be 1s1. So 1s and then a superscript with the 1 right there. So the first number designates the energy level that hydrogen resides in. So this is n equals 1. So n, the quantum number, refers to the row on the periodic table. So 1, this first energy level, that would be the first energy level outside of the nucleus. And its atomic number is 1. Right? So the atomic number of the neutral atom is equal to the number of protons as well as the number of electrons. There's 1 electron in the s orbital. So 1s1 there. Right, helium is over here, so helium is the second atom, so it would have atomic number 2, which is also 2 electrons in a neutral helium, so that's 1s2. Right, so now we're going to talk about how electrons are filled in an atom in their orbitals. Okay, so if you recall from chapter 2, we had a couple of different types of orbitals. We have the s orbitals that are spherical. We have the dumbbell-shaped orbitals that are the p orbitals. There's 3 different types. Basically, they're just on different axes: the px, the py, the pz, based on the position of the dumbbell. Okay, and then we had 5 different types of d orbitals, and then there are some really funky shapes that are f orbitals, and there's 7 different ones of those. Okay, and so remember that the orbital is just a mathematical equation. If you were to take the equation that represents that particular orbital and graph it, it would give you that particular shape. And if you shade that in, that's the probability in that area where you would be most likely to find an electron, okay, for that particular atom in that particular energy level of the atom. So remember, energy level, we're talking about n equals 1, the first energy level outside of the nucleus, n equals 2, the next one outside of the nucleus, n equals 3, and so forth. Okay? On the periodic table, these energy levels actually correspond to and equal the row number on the periodic table. So for example, hydrogen, this is n equals 1 energy level, right? So this is n equals 1 energy level, this would be n equals 2 energy level, n equals 3, 4, and so forth. So the atoms that appear in a particular row are going to have electrons that go out to that n number, okay, where it appears in the periodic table, all right? Okay, so the maximum number of subshells or sublevels that orbitals and electrons in any energy level can be summarized in this table below, right? And so each orbital can hold 2 electrons. So hydrogen only has an s orbital. There's only one type of s orbital, and therefore hydrogen, right? Well, hydrogen only has 1 electron because it's equal to the number of the atomic number, which is equal to the number of protons and the number of electrons, since it is neutral. Okay, so it only has 1 that goes in there, but helium, this is an n equals 1. Helium is number 2 on the atomic number, which is equal to the number of protons, which is also equal to the number of electrons because it's neutral. So n equals 1, okay, there can be a maximum number of only 2 electrons in that first energy level, and helium would occupy both of them there. Hydrogen would only have 1 electron, and it's n equals 1 energy level, which is in the S shape, okay, for the probability of finding it there. Okay, so at n equals 1, the number of sublevels is just 1, okay? The designation that would be present for the orbital in that sublevel is the S, and the S is in the 1, so we put a 1s in front of it, okay? The number of orbitals that we can have is only 1, and so since there's only 1 orbital, each orbital can hold 2 electrons, so 1 times 2, I can only have a maximum of 2 electrons in the first energy level, okay? So over here, we're going to kind of use this as we go. This is kind of showing you the energy level, kind of the map of how the orbitals are arranged in terms of energy. Okay, so here is the first energy level. This would be like outside of the nucleus. there's the protons, n equals 1. So this energy level can only hold 2 electrons, right? Okay, so then n equals 2 would be the second energy level if the atom had that number of electrons. Okay, that means that the second energy level out from the nucleus, there can be 2 sublevels. Okay, second energy level, 2 sublevels. The sublevel designation, now there is a S and a P. That's 2 different sublevel designations. Okay, and since it's in the second energy level, we say that's a 2S and a 2P. Okay, so remember the S, we only have one type of S. If it's 2P, we have 3 different possible P's because it's PX, PY, PZ for the orientation. Okay, so the total number of orbitals that we have there is an S, a PX, PY, PZ, so there's 4 total orbitals here in the second energy level. Okay, so how many electrons can be occupied out in the second energy level? Well, 4 times 2, each orbital can hold 2, 4 times 2 is 8. So in the second energy level here, n equals 2, we can have up to 8 electrons there. Right, so on the second energy level, which would be the second row on the periodic table, neon would have 2 in its inner on the first energy level and 8, up to 8 in the second energy level. Okay, any atom that is less than that would have less electrons here in their outer energy level. Okay, so let's keep working on through. The third energy level would be the third one out from the nucleus. Okay, the number of sublevels is 3. It's in the third, so we're going to have S, P, and D orbitals now we get, okay, in the third energy level. Okay, and they're designated as 3S, 3P, and 3D because they're in the third. Okay, we have only one type of S. We have 3 different types of P's, PX, PY, PZ, right? And we have D orbitals, and we have 5 different types of D orbitals, right? We have the, you know, that, and then like that donut shaped one. Okay, so 5 plus 3 plus 1 is a 9 total orbitals that are present in the third energy level. 9 times 2, we can have 18 electrons. If you were to, you know, do your dash here to get n equals 3, you can have 18 electrons in that third energy level. Okay, and then going on to the fourth one, and then we'll kind of just write a generic formula here for calculating electrons in any energy level. So the fourth one, we have 4 sublevels. We have S, P, D, and F. Right, so 4 different types of orbitals. They're in the fourth energy level, so they get designated as 4S, 4P, 4D, 4F. Okay, 1 type of S, 3 type of P, 5 Ds, and 7 Fs. So 7 plus 5 plus 3 plus 1. There's 16 different types of orbitals there. Each of these orbitals can hold 2 electrons each. So 16 times 2 gives me 32 electrons that can occupy in the fourth energy level. Okay, so for any n, it would be the n sublevel, and then here you can kind of see 4 is n, 4 squared is 16, 3 squared is 9, right? So you can kind of use this designation here for whatever the number of sublevels is, or the energy level as well. And then for the number of electrons, it would be 2n squared, like that. Okay, so let's go back over here to the second energy level. So the second energy level, we have an S and a P. The first energy level, we just had the S. So here's just the S, right? And so remember that staircase diagram that I showed you. When we go from the first energy level to the second, there's a really big jump, right? And so when you jump, the second energy level also has S and P there. So we start again with S, and then the energy level difference between S and P orbitals is just a little difference there, okay? But not a lot, okay? But there's a PX, a PY, and a PZ. And these are all equal to each other. They all have the same energy level, all 3 have the same energies, and we call those, they're degenerate. So sometimes you hear that word, the energy levels are degenerate. That means there's 3 of them, and they're all equal. We don't stagger PX, PY, PZ. They're all kind of in a straight line there for the same energy. Okay? All right, and so, you know, each of these orbitals, if we were to, you can see the color of my marker here. Okay. If we were to add the electrons, electrons are kind of shown by arrows. If we have a full electrons in the first energy level, then we would show that like that. Okay. We haven't talked yet why we're going to put spin up, spin down, but we would show electrons like that. Okay, and then the second energy level, right, we would fill them like this. So there's 2, 4, 6, 8. And then over here kind of corresponds, we have 8 that we have calculated. Okay, and then the third energy level, you're going to have 18. So you're going to have 2, 4, 6, 8, 10, 12, 14, 16, 18. So you can see the 3Ds are up here. So the 3Ds are actually a big jump between the P. They're actually higher energy than the 4 S's, but lower energy than the 4 P's here. Okay? And then the same thing happens with the 4Ds. They're actually higher energy than the 5 S's, but then they would be lower energy than the 5 P's, which aren't shown there. Okay? And so all of these electrons would just keep getting filled in there if it was an element that was, you know, really big or far down here in the periodic table, down in here. Okay. Okay, so I think that's pretty much it for right now for this. We will come back and continuously use this energy diagram because it will help us in filling and determining electron configurations. So when we figure out electron configurations, you may recall maybe from high school chemistry, you have 1s2, 2s2, 2p6, 3s2, 3p6. That's what we're doing here. We're filling these energy levels. So 1s2, 2 electrons, 2s2, 2p6 electrons, 3s2, 3p6, 4s2, and then we jump to the 3s, 3d10. There's 5 here, so we can have 10 filled. 4p6, 5s2, 4d10, right? And so that's our electron configuration as we build up on the periodic table, and we can do that for any different element. Okay, so we're going to kind of use this a good bit here shortly when we do electron configurations. Okay, the very last thing here, we can see that we can organize or rank the energy level. S orbital is lower energy than P. P is lower energy than D. And then D would be lower energy than the F's. For 4F would be way up here. Okay, so F is the lowest energy going up to P, D, and then F is the highest there. Okay, so we can represent an electron configuration with something called an orbital diagram, right? So down here we have the electron configuration for hydrogen, which was 1s1. It is in the first energy level, the first row of the periodic table. Those has an s orbital, and 1 is the number of electrons, which is equal to the atomic number. Okay, so this can be represented as an orbital diagram, and the diagram symbolizes the electron as an arrow, and then each orbital has a box or a line. Okay, so this box here is representing the orbital, and we will label it as 1s, or if you just kind of shorthanding it, the line represents the orbital as well, labeled as 1s, and then this would be the electron. So you should kind of show that as like a half arrow, and the direction of the arrow represents the orientation of the electron's spin, right? So electrons can have magnetic fields, and so it can be a spin up or a spin down. Either you're going with the magnetic field or against the magnetic field. And if you have 2 electrons in an orbital, for example, the s, you have 2, one will be spin up, the other will be spin down, so that they cancel each other out. Okay, so the spins must cancel in the orbital whenever they're paired. It means 2 electrons have opposite spins. One is going with the magnetic field and the other is going against it. Okay, so we can represent an electron configuration with something called an orbital diagram, right? So down here we have the electron configuration for hydrogen, which was 1s1. It is in the first energy level, the first row of the periodic table. Those has an s orbital, and 1 is the number of electrons, which is equal to the atomic number. Okay, so this can be represented as an orbital diagram, and the diagram symbolizes the electron as an arrow, and then each orbital has a box or a line. Okay, so this box here is representing the orbital, and we will label it as 1s, or if you just kind of shorthanding it, the line represents the orbital as well, labeled as 1s, and then this would be the electron. So you should kind of show that as like a half arrow, and the direction of the arrow represents the orientation of the electron's spin, right? So electrons can have magnetic fields, and so it can be a spin up or a spin down. Either you're going with the magnetic field or against the magnetic field. And if you have two electrons in an orbital, for example, the s, you have two, one will be spin up, the other will be spin down, so that they cancel each other out. Okay, so the spins must cancel in the orbital whenever they're paired. It means two electrons have opposite spins. One is going with the magnetic field and the other is going against it. And this is called the Pauli exclusion principle, when the spins must cancel in the orbital when they're paired. And it means that two electrons have opposite spins with each other. All right, so hydrogen, it would be like this. You have a box, that's the orbital for 1s, and then there's one electron in there, or you can show it with the line here. We go down here for hydrogen and show it for, or sorry, not hydrogen, show it for helium. Right, so helium is also 1s, there's two electrons. You'd have a spin up and a spin down if you're showing the box notation, or if you're just showing it with the line, you show it like that. Okay, so we're going to talk about this energy level diagram here shortly, and over here we kind of just show the lines just to simplify that a little bit when we do that. So speaking of helium, did you hear about the chemist who was reading a book about helium? He just couldn't put it down. Right, so our energy diagram kind of explains, again, how the electrons fill the orbitals, right? And we can kind of see that I mentioned previously that the splitting occurs, right? So how these are different, higher in energy. And the main splitting that we're talking about here is that we have splitting between the 3 and the 4, how these 3D orbitals are actually higher in energy than the 4s, and the 4D orbitals are actually higher energy than the 5s there. Okay, so there's actually two main reasons why the splitting occurs that is seen and represented in the energy diagram. The first one is the outer electrons in the atom, right? They're negatively charged, and the nucleus is positively charged. So those electrons are being attracted to the positive nucleus. Opposite charges attract, right? However, right, okay, so that's called penetration. So the electrons are trying to attract in closer to the nucleus. However, it's kind of versus or up against this other factor, which is there's a whole bunch of other electrons here in the same energy level, right? And they're all negatively charged. And so when they attract in, then they're kind of repelling against each other, right? So the second one is repulsion of, one electron with the others in the same energy level. And this is called screening and shielding. So if the screening and shielding is a large factor, then it's going to affect the electron being attracted into the nucleus, thus it's going to stay bigger as an atom. Okay, if it can't attract in because there's a lot of shielding going on, then the atom will remain bigger. If there is less shielding and the electrons can be attracted into the nucleus, then the atom will be smaller. Okay. All right. So so again, we have starting with 1s, the first energy level, right? And as we fill orbitals, as an atom gets bigger and bigger and has more and more electrons, we always fill from the ground state up. So we're always filling from the lowest energy level, S, and then filling up the energy diagram. Right, so the way that the electrons get filled for the electron configuration is going to go 1s and then 2s, and then the next energy higher is 2p, and then 3s, and then, oh whoops, I made a mistake there. So after 3s is 3p, and then we have 4s, and then we go to 3d, and then we go to 4p, and then we go to 5s, and then we go to 4d, and so forth, right? So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, and so forth. And then you have your f's in there, and then you get up to the sixes. Okay, so just kind of a little joke here, right? So again, we call that this lowest energy level, we call that the ground state. So why does a hamburger have lower energy than a steak? Because the hamburger is in the ground state. Yeah. Right, so we're going to practice a little bit more for determining electron configurations for electrons in atoms. So we're going to write the electron configuration and also the orbital diagram that is represented by that configuration. All right, so first one we're going to take a look at here is lithium. So I would kind of get your handy dandy periodic table just so you can kind of see, lithium is right there, it's number 3. So lithium is number 3 on the periodic table. Right, so that's the number of protons. It's also the number of electrons because it's a neutral atom. So we have 3 electrons. And we're going to start here with our energy level diagram, right? So you have a copy of the energy level diagram that looks kind of like this, so you can pull that out as we go through. So you're able to kind of use that as we go along on your end. Okay, so lithium, we're going to fill from the bottom going up first. All right, so lithium has 3 electrons, so 2 of them are going to go in the 1s, right? So we have 1s2, right? And then we have the third one is going to go in the 2s right there. So 2s1. So we can say, see 2 plus 1, right? We have 3 electrons right there. Okay, so 1s2, there's 2 electrons there. When they pair, they have opposite spin. And then this 1 electron is represented just 1 there in the 2s box. Right, so remember in the s orbitals, we can only have 2 electrons. And in the first energy level, all we have is an s-type orbital. Right, so in this n equals 1, there's 2 electrons flying around just in that first energy level in that S shape for the probability where you would find them. And in the second energy level, right, there's also an S distribution and there's just, 1 electron out there. Okay? All right, so let's take a look here at carbon, right? Okay, so carbon is number 6 on the periodic table, so that means there's 6 protons as well as 6 electrons. All right, so we're going to fill again. So 1s2, I can put 2 electrons right there in that orbital. And then we have 2s2, 2 can go there. So that's a total of 4 so far. And then I can put 2 in the 2p. So 2, 4, 6. 2, 4, 6, 6 electrons there. Okay? Okay, so when we go to represent that in the orbital diagram, 2 there for the S, 2 there for in the first energy level, and also 2 in the second energy level for the S's. And then for the P, there's 3 different types of P's. Okay, so we need to use something called Huns Rule so we know how to distribute the electrons. So when filling orbitals that have the same energy, they're degenerate. Remember, this is the px, py, pz there. They're 3. They're all the same energy level, so they're all kind of equal. You're going to place 1 electron in each orbital first before going back and completing pairs, right? So I would put 1 electron there and 1 electron there. I wouldn't fill the first one first. So if I had more electrons to put in, I would put the next one there, and then if I had more, I would go back and start doubling and pairing them up. Okay? So here we say that carbon has 2 unpaired electrons. Okay, so there's 2 unpaired electrons. And that's going to be really important because the number of unpaired electrons actually gives it a specific property. Okay, and what you're going to find out here shortly is that carbon, right, all of these atoms that are in the carbon family, all of them are going to end up having the same number of unpaired electrons. In the nitrogen family, they're all going to have the same number of unpaired electrons, whatever that is, in the oxygen, the fluorine, and the noble gas columns as well. Okay, and that's going to dictate and explain their reactivities. Okay. All right, so we're going to take a look at a couple more examples. We're going to write the electron configurations, the orbital diagrams, and we're going to determine the number of unpaired electrons for the following. So the previous example we did lithium and carbon. So I went ahead and left them in there. So I just want to pull up the periodic table and show you where we're at on the periodic table. So we're doing lithium, and then beryllium, and then boron, carbon, nitrogen, oxygen, fluorine, neon. So we are going across the second row of the periodic table, okay? All right, so let's do beryllium together, and then boron, and then I'll pause and give you a few more minutes to do these ones on your own, and then we'll check the answers and then talk about a few things, okay, before moving on. All right, so beryllium is number 4 on the periodic table. So it has 4 electrons. So it's going to be 2 are going to go in the 1s. So 1s2, 2s2. So it's right after lithium. So lithium's number 3, beryllium's number 4. So now we're going to have filled 2s. So here is the 1s and the 2s. And here we have 0 unpaired electrons. So it's happy. There's nothing here that needs. Okay. Take a look at boron. So boron jumps over to column 13. That is number 5. Okay. So 5 protons, 5 electrons. So we have 1s2, 2s2, and then that's 4. 2, 2, and then 1 is going to go in one of these 2p orbitals there. Right, so here we have 2 go in the 1s orbital, 2 go in the 2s orbital, and then over here is my px, py, pz, and I just have a 1 that goes in there. So here I have 1 unpaired electron there. All right, and then the carbon is number 6, so that is 6 protons, 6 electrons. Oh, I'm sorry, this is not right there. I should say there. So 2, 4, 6 total electrons. This is the one that we previously did. 2 get filled there, 2 get filled there, and then we use Huns Rule, and we separate them out. We're going to fill each one individually first, and so we have 2 unpaired electrons there. Okay, so go ahead and pause the video and finish the remaining nitrogen, oxygen, fluorine, and neon for the electron configurations, the orbital diagrams, and figuring out the number of unpaired electrons. Okay, so we left off with carbon, and we have the nitrogen, oxygen, fluorine, and neon that you can check your answer with here. Right, so nitrogen is 1s2, 2s2, 2p3. We get an extra 1 as we're moving across the periodic table from the left to the right. So carbon, neon, gain an electron for the atomic number. Right, and then so we had 2 unpaired electrons here. Here we have the 3 electrons in the 3p. So there's 1, 2, 3 unpaired electrons there. Oxygen, again, we're just going across the periodic table. We gain another electron. So there's 4. So now we go back and double up in the p orbital there. And so we have 2 unpaired electrons in the p. And then fluorine, we're now in the halogen column, right? So moving across again, we add another electron in the p. So these are all full. So now we only have 1 unpaired electron. So halogen column, right, that's number 7 on the periodic table. We also have 7, we have 9, 9 total. We have 7 in row number 2, but then we also have 2 extra electrons from the first energy level in row 1 that gets added in there. So the halogen column, right, this is very reactive, right, because it only wants 1 electron. So it's going to take that from something else. Remember, to the right of the staircase, these are nonmetals, and nonmetals gain electrons, or they'll share if they form a covalent bond. So they want to gain electron because they want to be full. They want to have a full shell there. Okay, so they're very reactive because they only need 1. And then neon is our noble gas column there. So you can see it gets, we have 10. So 10 electrons. So 6, 7, 8, 9, 10. 10 total electrons here. 2s, sorry, 1s, 2s, there's 4, 5, 6, 7, 8, 9, 10. So the whole entire second energy level with the first is full here with neon. That's column 8 or 18, and that's a noble gas, right? And has 0 unpaired electrons. So that means it's not reactive. It doesn't need any more. It doesn't want to react with anything or give anything up because it's very happy. So basically, you know, I always have this saying that, you know, all atoms want to be a noble gas. They want to have noble gas configuration, meaning they want to gain or lose electrons to have noble gas configuration, right? Because then they're very happy. They're very stable, low energy when this is, their shells are all full, okay?